Uh, Dear participants, our next talk is on graph neural network and graph convolution network by Dr. Dinesh Singh. Dr. Dinesh Singh is an assistant professor in School of Computing and Electrical Engineering, Indian Institute of Technology, Mandi. Prior to joining IIT Mandi, he worked in high-dimensional statistical modeling team with Professor Makoto Yamada as a postdoctoral researcher at Riken Center for Advanced Intelligence Project AIP, Kyoto University Office, Japan. He completed his PhD degree in computer science and engineering from IIT Hyderabad under the supervision of Professor C. Krishnamohan on scalable and distributed methods for large-scale visual computing. He received his MTech degree in computer engineering from NIT Surat, where he worked with Professor Dhiran R. Patil on machine learning and approaches for network anomaly and intrusion detection in the domain of cyber security and cloud computing. Sir, can you please deliver your lecture, sir?
Thanks, Dr. Rakesh, for the introduction. So I'm just connecting my this iPad. So soon I will present it. Dr. Rakesh, I need to disconnect for a moment in order to give some permissions to share. So I will rejoin in 1 minute.
No issues, sir. You can please.
My screen is visible now, right?
Yes, sir. Visible.
Got it. So, okay. So, good morning, everyone in the audience. And my introduction is already given by Dr. Rakesh. So, today I'm going to talk about this graph neural networks. And not only the graph neural networks, so same way like nowadays we are doing deep learning on images and in natural languages or any other domain. But prior to deep learning, we have this uh, simple machine learning models, or nowadays we call them traditional learning algorithms, or in some models we call them shallow models. So same way, what are the shallow learning techniques on the graphs prior to this graph convolutional neural network or simply graph neural networks? So let's start with that one. So my introduction is already given by Dr. Rakesh. So here at IIT Mandi, I'm heading this visual intelligence and machine learning group, where we are doing all sorts of machine learning and computer vision based tasks. So, just one minute. Yes, मैं दे रहा हूँ. Sorry. Yeah. So uh, in that we are doing all sorts of like this learning based task, or the computer vision based task, including learning over the graphs. Let's skip this one. So today's agenda is like that. First of all, I will simply talk about the graphs and some of the graph applications, most probably in the like analytics domains, where we wanted to perform some task of clustering, or like classifications, link prediction, these kind of things. Okay, then what are the shallow techniques we were used to apply prior to this graph convolutional neural networks or graph neural networks. Then few flavors or few models in the graph neural networks, I will talk about them and exactly like how their journey begins. Then on top of that, like not only we are going to talk or we need to just perform certain tasks on the graph, but we also need to know whether exactly they are learning some relevant information or not. So means the explanations of the graph models or graph neural network based models, that is also very important. And in that series, I'm going to present my own work, that is the graph line. So which once you have some graph neural networks, you can dig out certain features, and you can say that, okay, so this kind of information which is has high correlation with our target variable. So, and that's why these neural networks are learning good features in that series. So now let's come to the what are the graphs, if we simply ask, and what type of graphs are there. So there are numerous applications where rather than capturing this what you can say that relation based or the tabular data is losing lots of information, while networks can have all those kind of information, and primarily this information is a structural information, right? So let's say uh, we have several like researchers, and some researchers are we can identify them, we can record n number of information about that researcher. Okay, how many patent they have, how many publications they have, how many students they graduated, and how many are still doing, or where they are publishing, with whom they are collaborating. Okay, so with the collaboration also, that becomes a link here, the researchers becomes node. So if we simply see the researchers, then we like lose lot of information. Now, as I said, that collaboration is a link, but again you can define that link also. So like how many joint publications are there, how many joint projects are there, how many joint scholars they are taking. But Now these two informations, the collaborations information and the researchers its own information, they have something larger than their sum. Okay, so sometimes in the machine learning community, the sum of two elements or the union of two information is always larger than their things, and mainly within that category, this is structural information is the key players. So if we are not using this structural information, so very vital information we are not capturing. So, and that's also applicable to like other applications. So all of you are using this Google Map, and there how they are finding the different routes, and based on some graph optimization, finding shortest paths, again places they are representing through nodes. So that also can be represented into the graph. Again, when we are going to the deeps into our traditional sciences like biologies and chemistries, so there also the molecular structures we have. So we have numerous atoms, and there are bonds between them, and also in the 3D space they have some orientations. Okay, and all those things are actually defining the property of any chemical compound, whether it's magnetic, it's acidic, it's basic, it's alcoholic, whatever classifications the traditional like chemical researchers is doing, that we can represent through graphs, and then we can identify, we can learn the patterns. If this kind of patterns are there, or this kind of structures are available in a new molecule, so most probably without having the real experiment, we can predict certain properties of chemicals. So as well as in the biology, nowadays graphs are widely used to represent these protein-protein interactions, and then we need to perform certain clustering and then identification of this one. But how we actually represent that, that is all sorts of like those who are in the audience from this computer science background or similar programs, they have done this data structures, and we cover a like lot of about this data structure things, how to represent the graphs. So first thing is how we can represent the graph into the computer memory. So mathematically, if you see here, so a graph is nothing but a set of two further sets. Those are V and E. V are generally represented as the set of nodes, and E is the set of edges. Okay, so now further we have two ways to represent this E actually. We can we normally represent through a simple array, but for E we have the adjacency list and adjacency matrix. So let's say, so here is a one example graph. So where A, B, C, D, E, those letters representing the nodes, so they becomes the set B. Then how they are connected, so smaller letter first, this is a undirected graph, so AC also say that, okay, then CA is also a like graph, but in directed one, we need to specify both if they both links exist, right? Then on edges also, either they can be simply 0 and 1s, or they may have some weights, so that defining the significance of the link, right? Now, again, as I said that if let's say this is the researchers, we can have so many properties of about simply with this node E, so that we can represent. Let's say there is another example from this protein graph. So where we have some residues represented through nodes in letters. Then everywhere we have some protein sequences, which were we got through our sequencing techniques. Now, what are the links? So links are, if in the real space, in the molecular structures, if their distance is less than certain, threshold, which is generally the 5 or 6 angstrom, which is a very less distance, then we consider there is a interaction between these residues. And this way we can define the graph. So now we have the graphs and we have the features of the graph, and as well as their interactions we are representing through either adjacency list or through a adjacency matrix. And computationally, few are better in certain cases, and the other is better in other cases. So that is purely a like data structure point of view, how we actually represent the graph into the memory. So then there are so many applications we already counted. So we can use graphs for social network analysis. Okay, what are the similar communities in the on the Facebook? So then all of the persons are actually the nodes, and the properties of a person, they are actually their features. Then with whom they are connecting, and based on those connections, we can define a graph. So then, based on the similar kind of peoples, based on to which crowd they are connected, we find out the communities. We can identify the sentiments of their comments, and based on that, even we can give the label to the community, whether the community is some activist community, the community is a political community, community is a student community, community is a researchers community. So based on this kind of analysis, you can do. Similarly, on the e-commerce networks or biological networks or even traffic networks, you can perform all those kind of things. So anywhere, wherever you can represent the domain knowledge on in terms of nodes and the edges between them or links between them, and here everything can have features. A node can have features, an edge can have features. Okay, and that's also either univariate or multivariate features we can have. Okay, now what kind of task we can perform on this kind of things? So we can also do the classifications or the clustering or anything else. But first question comes, how we can do, let's say, the classification. So if you remember, prior to the graph neural networks, support vector machines or this convolutional neural network or neural network support vector machines and kernel based methods were like state of the art maybe in 2000 to 2006, 7, or maybe later till 10. Okay, so if you can define a similarity matrix on two graphs, so let's say there are two graphs, G1 and G2, how similar they are. If you can quantify that, okay, so then we can use that particular function as a graph kernel into the support vector machines, and we can define it. So in the support vector machines, by default name vectors, so means generally it works on the vector data. One way is we can extract some vector data, then we can use that into the support vector machine. But if whatever vector you are generating, that is not capturing the structure well, or only once we hard coded it, then we have the like limited scope of improving based on the structure. So whatever structures once we use, then we cannot use. That kind of problem was there. Then how we can inherently exploit these structures? Okay, not only the features or the node features or the edge features, but everything what we have on the nodes, we can like start learning from that one. So now this is a very simple kernel. So now here we have two graphs, and now by simply through bare eyes, we can say that okay, a lot of similarity is there in this graph. Okay, so few nodes we can supple, and then it will be more. But how we can quantify, how we can tell what is the similarity, how much they are similar? Is it 10% similar, 20% similar, or 80% similar? Okay, so for that, let's say now we come in here. If you see, the first task is through graph isomorphism. So this is the standard graph algorithm. So it can find out a largest subset or subnetwork within these two graphs, or largest subgraph between these two graphs, which is common. Okay. So then, based on its cardinality and the joint cardinalities of these two graphs, we can like normalize that into 0 to 1. Okay. So this is our ratio of the similarity. But this problem is a NP hard problem. And now if we put, let's say our graph is significantly large, n is significantly large, and complexity is n to the power 10, 20 something. So then it's huge. We cannot use, we will just busy into computing the similarity between these two, or just finding the largest subset. So that problem can give a very right answer, but not applicable here because of the this computational complexity, and this is NP hard, so even using it not a good idea. So then research community started developing graph kernels. Same as for the support vector machine, we have Gaussian kernels and polynomial kernels and all other kind of kernels. So in the graph kernels, we have several graph kernels. Let's say few examples are shortest path kernels, or random walk kernels, or WL kernel, or deep graph kernels. So these kind of kernels were there. So here, this is one example of WL kernel. So the task is very simple. So these graphs are at the initial, at the original space. Okay, so how many are the, what is the union of the nodes? So here all the nodes are labeled from 1 to 5 in both the graph. Okay, so now we can start counting. So this 5G1 is nothing but the transformation of graph from graph space to the vector space. So this vector we are actually building for this one graph. So how many, what is the frequency of the nodes within this graph? So that we simply represent for the graph 1, then graph 2. Similarly, now they are in the vector space, but that is the only we count the frequency of the node, where is the structures. So for that, we will do the relabeling of the nodes kind of thing. So let's say that node 1, who are the neighbors of the node? So of course 1, it has the label neighbor 4. So that is our kind of, now we included its neighborhood within that one. Now this is our new node 1, 4. Similarly, for another one, it's 1, 4. For 4, it's 2, 1, and 3 and 5. These are the neighbors. So now we are using the adjacency matrix, or the structure, how this node is connected with the other nodes. Now these are our new actually nodes in this graph. Similar operations we are going to perform in the another one, and this is actually called a Westphaler-Lehmann test, where we keep doing this process up to certain number of times. So now again, we can instead of keeping this complex node structures, we can relabel them from 6 onwards. So actually this is the nodes and their neighbors. Then we can start giving them the new labels. Then again we can count the frequency of those nodes. If you see, the number of nodes may be different, and their occurrence is also be changed, right? And this way, after certain times, whatever is the like inherent structure into these two graphs, that will be captured through our this transformation phi of G1. And this one good vector, we got it, and then through its dot product, we can define our graph kernel. Okay, so now we got a like kind of measures, we can normalize it in between 0 and 1, we can get our graph kernel. So this was the like very popular in this one, and very standard libraries are nowadays available to apply the graph kernels wherever data is very small, so they are still performing much better. So you guys can try those things, and in those libraries, significant number of these kernels were already implemented. So if you are there in these examples, so you can try that. Once you can define the kernel and you can calculate your gram matrix or the kernel matrix, you can apply a support vector machine over this one or any other clustering or any other classification matrix over those vector transformations, and you can achieve your task. But still, and they are actually quite popular. So I mainly work in the computer vision domain. So in the computer vision also, so image and videos you can sometimes represent through the like graphs, and that comes how we can represent video or image into the graph. And once we have those graph structures, all sorts of this graph based learnings we can apply. So these are two of my works, which one is presented in pattern recognitions, where actually whatever activity is there in the video, we represented that activity through graphs. So let's say you see there is a video and something happens. So the crowd started running from here to there. And once they are running, so the edges are actually representing whether this is the same person running towards each other, or whether there can be a collision between two different peoples. And once we have this kind of graph, so we can learn a classifier whether this is a normal activity or this is an abnormal activity, right? So human activity recognition is a very important task in computer vision. So we are able to do it, and it works much better. In 2017, this work we did, and here we are using this graph kernels. Even they are performing much better given the limited amount of data. But for the action detection task, when we have significantly large number of samples, at that time using the graph neural networks works out much better. That I'm going to talk about the further. But the way of representing the actions is almost similar, but here we use some deep learning techniques to represent the features as well as whatever are the graphs, then performing using graph neural network kind of things over that. Okay, now let's coming to the deep learning. So this deep graph networks, or this convolutional neural networks or graph neural networks, they were came after the success of the deep learning. So deep learning was giving very good success in the NLP, in image, and nowadays we have LLMs and several types of tasks on the computer visions. But when we are simply asking, can we apply all those deep learning techniques on the graph? So in the old days, the answer was no, we cannot apply. But recently, after 2017, several techniques came where they focus on how we can apply those deep learning based methods onto the graphs. So even the previous example of graph kernel, what I showed, so that gives one hint how we can use the different layers to compute the different level of information. So first we did one test, again we did another test, we get the different type of nodes and their different frequencies, then we keep doing it repeatedly. Okay, so means this kind of layers we can define, and even people propose some graph neural network structure based on that principle. Okay, but when we are applying this graph neural networks for the, or the deep learning methods for the graphs, so then we face certain issues. First one, the irregular structures of the graphs or the geometric deep learning problems. Okay, so it's not as simple as our tabular data we can apply. So we have nodes, and some has many edges or many neighbors, few have very limited or one or means not that well connected. Okay, so this is complete irregular. And even sometimes graphs are like homogeneous. If let's say I say, okay, so there is only the researchers only, and we are actually making a graph among them. But like you can take another example. Sometimes they can even node can be heterogeneous. So let's talk about the researchers and research articles together. So we have research articles written by many authors. We have authors who have written many articles. So articles are the nodes and the researchers are the nodes. Okay, then where they are published, even the publications are the nodes. Okay, and then we have this kind of network becomes our heterogeneous networks. Even how we can apply the graph neural networks on the heterogeneous graphs, that is again a very big challenge. Then, of course, large scale graphs. So, if we talk about nowadays the social networks, the Facebook, LinkedIn, they have millions of users, which are going to be a node. Then billions or trillions of edges among them. Okay, so that is the scale of the graphs available today. So how we can scale these methods on such a large scale, that's again a very big challenge. Then incorporating interdisciplinary knowledge, because now in almost every domains graphs are possible, and when you are designing a deep learning techniques, whether whatever is the domain knowledge available there, so you applied that correctly or not. It's not like one graph neural network you define and it can work universally. So based on the whatever is the knowledge we have, so prior to designing a method, we should have some interdisciplinary knowledge about all those things. So let's say I give the example of this protein network. That's also different biological problem than chemical things. They have different social networks, are different domains. So how we can design some generalized networks which can be used on almost all those things with little fine tunings. So those are the big challenge. So, but nowadays neural networks are handling quite well. So let's move towards them. Now, based on the what type of task you wanted to perform and how this entire domain is evolved, so we have variety of graph neural networks. So first in that was the graph recurrent neural networks, or simply known as graph RNNs. So they were initially developed, and mostly the task was just either feature learning or just classifications kind of task. Obviously, this they have some limited uh, scope, or have a lot many challenges due to the this vanishing gradient problems in the recurrent neural networks. So then graph convolutional neural networks came, but the bigger challenge was how we can define a convolutional operations, which was actually meant for the spatial domain only. And while there is no regular structure, so finally how we can apply the graph neural network, that I will talk a little bit about that one. Then obviously the nowadays we can see the graph autoencoders or the reinforcement learning based graph models, as well as the generative graph methods. So same way we can generate today the images based on our generative adversarial networks. So same way can we generate the new graph. So let's say we have certain chemical compounds, can we generate new molecular structures with certain properties, right? So these kind of or these are the various types of GNNs which were proposed so far in the literature. I'm not going to talk about much about all of them. So but initially tools I'm going to cover almost in details. Okay. So then task, obviously, when we are given the graph, so let's say social network graphs, they are actually single graph. So what we generally do, we perform the task on the nodes, either the classifying a node, whether this particular person in the LinkedIn is a student, is a engineer, is a computer vision scientist or something, like, or a link prediction. So these are the two researchers. Is there is any possibility that they are collaborating or they have some interconnections between these two? So these kind of things we can do. Obviously, that Node recommendations. So nowadays, like you can see the Netflix, they are also having, okay, who are the watchers, who are the videos, and there is a graph. If they watch these videos, okay, so whether that another video that going to we can recommend to them. So now video if represented through this, whether we are going to recommend this node to particular community or not. So this kind of task you can perform. So either you can perform any machine learning task on simply based on one node, and it's obviously when we are talking about the graph, so it's adjacency, how it connected with the other nodes, that's going to be taken in account into that one to present. But we can like perform task for the nodes, and most of the this networks when we design, so they are node focused. But we can also do certain tasks, like the entire, like in the chemistry we were saying that, okay, this is the graph of a molecule, but now we do not want it to define the property of a molecule, but we sorry, of an atom, but the overall molecule, so whether it will be magnetic or not. Okay, so the task can be on graph based, like in the previous examples of when we are actually representing uh, a video activity through graphs. So here it's not the individual actor we are representing, his anomalous or his miscreants, but whether the activity is altogether abnormal or not. All peoples are normal, but whether their activity is abnormal or not. So entire graph we need to give a label, so that way we can also learn the graph classification task over the entire graphs. So now we have multiple graphs, and for we are telling the character of one graph. Okay, so this kind of things we can do. So we can generate new graphs and all other various kind of properties of a graph based things we can use. So let's say, so these are the structures. So what is the cluster of the acidic compounds? So this kind of task we can perform at. So now from this one, what we can do, so whatever this graph neural networks, we can apply them for the node classification or the graph classification for both. So let's see how exactly this graph neural networks perform all those tasks. So far we talk about like what task we can do or how we are going to represent the node into the computer memories. So once you have all those nodes, edge or edge weights or node features, edge features, so we are going to take care of them. In that series, I'm going to explain this graph sig, which is you will find out somewhat very similar to what was the graph kernel initially I gave. So same on the same philosophy, a neural network is designed to predict the features and subsequently the class labels. And now, like if we, most of you, once you started machine learning, so you learn, okay, there are supervised algorithm, unsupervised algorithm, or reinforcement based things. All these kind of loss functions you can define for neural networks too. But let's start understanding how neural network works. Let's say within, first we will decide what is the neighborhood. So this is a graph. Now we are just seeing it in terms of means with the reference of a one single node. Let's say this node we wanted to explain, or we wanted to learn a representation for this node, so that we can use any kind of machine learning or any other analytics to perform certain tasks with this label. So we need certain features. So, but its character is actually also defined by with whom it's connected. Okay, so those who are directly connected, we generally call them, okay, so this is the first neighborhood, or hope 1, and this is now the second degree neighborhood, k equal to 2. So now these all the nodes are actually connected with the nodes which are directly connected to the node we are considering at this stage. Okay, so there is no restriction how much hope we can do, and the problem remains same as like the question in the KNN problem, what is the K? So again, same it is a hyperparameter you need to tune. But sometimes even using k equal to 2 can gives you very large number of nodes, and you are not able to manage. Let's say here, if you see only those colored nodes are picked, while these white nodes, they are also in the range, but they are not considered. Why? Let's consider about the Facebook. So you are considering one person. First, you are simply seeing their friends. Okay, let's say this person has 1,000 friends in his friend list. So now these are 1,000 nodes and 1,000 feature embeddings we have initially with them. Okay, so even this is a huge, but now let's assume all these 1,000 peoples further have 1,000 friends. So how many nodes in the second neighborhood? So it's almost 1 million nodes in the second neighborhood. We cannot consider all of them. So then Monte Carlo based operations, so we are going to perform some sampling over them. Okay, so out of those 1,000, how many we are actually picking just at a one time? And this now gives us a very good this randomization strategy we are using in the sampling. So it also gives very it leads to this generalized model learning. Okay, so same way like we do data augmentations, we took this image, and at certain times we dropped this neurons in the dropout layers, and now we are forwarding it. Okay, so even based on the partial informations, we are able to learn in convolutional neural network. So same strategy we apply when the number of nodes in the neighborhoods are very high. So we apply the random sampling strategies to pick few nodes at every times. Okay, so during the learning, it's not like we did that fix. So once we did one sampling, another epoch, another sampling. So this way, all the nodes are incorporated, while still the computational complexity is managed in very, very large networks. Okay, so now let's coming to our graph algorithms. So we have graph, we have nodes, so we can start. Let's say initially we have xv, the features vector of node v, which were originally given on the nodes. Okay, so and some nodes v, which are in our node set capital V, what you can see. Okay, so now we started k equal to 1 to k. So now this is simply our iteration. So don't mislead this k with this one. So this is actually a different k. So this is hop. So here it's you can think this like epochs. Now in the internal network, if you see what we are doing, so for each v in v, so for all nodes we need to learn the embeddings. So for every node we need to repeat this loop. So h, k, and this n curly n v, that is representing our neighbors. So this is the embedding or the feature vector jointly learned from the neighbors of the node v. Okay, so now here we need to define some aggregator functions. So they can be any functions: concatenation function, average function, max pooling functions, whatever you wanted to use, you are free. But let's say some aggregation based operators we are using. We can use one type of aggregator functions, or we can use different type of aggregator functions jointly in one layer also. That's up to your choice. So like we use different kind of filters in convolution neural networks, so you can freely use different kind of aggregators. Okay, so let's say now talk about kth aggregator within that one. And now you can consider even let's say so these are the iterations, but at the end when we are talking about in terms of deep neural networks, so they are becomes, let's say this is one layer we are applying, these are different filters, and now we stack that, we iterate that many times, so that becomes a deep neural network of k layers at least. Okay, so you are all those nodes in the neighborhood. We jointly, whatever h u k minus 1 in the previous iteration, whatever features was there, and that is was initially like initialized with the original embeddings given to us. But now we are learning much better embeddings at the end. So whatever is the previous embeddings, we perform some aggregations on those neighbors and we get this HN. So similar kind of embeddings we also have for our current node V. Then we kind of concatenate all those, the embedding of the node and the embedding of the neighbors. And but how much importance we should give and what are the weights on that one. So here we are using some trainable weights wk. So this is our weights parameters. Now whatever is this joint vector of the node itself and the neighbor nodes, based on that we are going to apply this weight matrix. So now you think, so you are given an input vector in the neural networks, and this is the weight of the connections with the hidden layers. So once we multiply whatever this input is there, it will transform to the your new hidden layer. Okay, so now we have this hidden layer at the end. We can after learning it for all the nodes, and then with for each node we can actually normalize it to a unit length vector, so that it will not the values won't go too higher, right? And with different k, so every k we have different aggregator functions within it, and then the different weight matrix with it. At the end we get our z. Now you think about this entire network. So here the original x vector, which is a node embedding, we are actually passing into our networks. So each layers based on its neighborhood where it's incorporating the structure of the graph. Okay, so which is coming from our adjacency matrix, who are the neighbors of the U, and then with different aggregator functions that act like different activations or different kind of different kind of filters in the our networks. Then the whatever weights, and now it's a linear weights, then we can apply whatever activation functions you wanted to use, either sigmoid or ReLU or 10H or any other kind of activation function you can apply. Okay, at the end you get your Z vectors. Now you can define your loss functions. So either you have a label of that particular node, so you can directly connect a softmax layer and you can train it in supervised way. If you do not have, you can define your unsupervised way. Let's say similar kind of nodes should be similar to each other, while those are not similar, so they should be far enough kind of things. Okay, or the other strategy like within this function is applied. Okay, so if they have the connections to each other, so then they should be similar. If they are far enough and they do not have direct connections, so then we should discourage the similarity. Okay, so if the nodes are neighbors or connected, then we should increase the similarity. Otherwise, we should discourage the similarity. So this way we have two functions. So one is with the positive sigma, while with the another negative sigma. So this way, finally, we can have we can define our unsupervised loss also, or reinforcement loss also you can apply, and thereafter same back propagation algorithms you can back propagate, and you can iteratively train all those weights, right? So this way we train actually the neural networks. So now if you think this entire phenomena, this is very similar to the graph, this WL graph kernels, but now instead of that we are using the trainable weights and non-linear activation functions and different kind of aggregator functions with different neighbors. Okay, so the end embeddings, what or the end features we are learning, they are very much in alignment with our target variables if we are using the supervised learning, or if we wanted to learn some task invariant embeddings for nodes, so we can define some kind of unsupervised loss, and with that we can train all those parameters. Okay, so that is like very initial method in the graph neural networks, and this work was published in NIPS in 2017. So you should follow if you are interested in learning more about this kind of methods. So now let's move towards our graph convolutional neural networks. Okay, so if I believe all of you are aware of convolution operations in the images. So we have some filter, and let's say here, so we have a filter. This is the input image. We have filter of 3 cross 3 size. We element wise multiply filter values with the image, and then we take a sum of them, and after applying some non-linearity, actually we place that into the new feature map, where each of these pixels are treated as a new neurons within that. Okay, so that is the convolutional neural networks on the grid structure kind of things, which are actually the images or the here. Spatial, what are the good things? So here, each pixel has predefined, okay, neighbor. So let's say we are taking 3 by 3 this filter, so, and this, this pixel is our center point. So this center point has fixed 8 neighbors. Okay, so we cannot have less than 8, or we cannot have more than 8 neighbors for a 3 cross 3 filter. So means our neighbors are fixed, and they have certain meanings, which is our spatial information. So what is around the surrounding pixels? Okay, so surrounding pixels, there are higher probability they belong to the same object. Okay, so that kind of things are there. But when so we can simply treat this as a graph. So this is sample node, and these are the neighbor nodes. But if that kind of a fixed architecture is there, we can happily apply convolutional neural networks. But that's not that straight forward. Okay, so if you see, so this is the update what we apply. Okay, whatever is the weight matrix and whatever is the inputs, we simply did the element wise multiplication, and then take a sum, and then we can apply our activation functions. So then this particular things is available. How we can apply that on the graph neural networks? That is very challenging, because irregularity is there. Irregular structures are there. Sometimes one node, sometimes 10 nodes, sometimes 100 nodes. But how we define in that case? So now our weight matrix is actually of the size how many total nodes are there in the input. But now if input is not defined, as well as now here these pixels and these pixels have a relative positions, and that is fixed, and that also have some spatial meaning. But in the graph, the location of the nodes, if this node is swapped with any other node, so that outcome should remain same. Okay, so outcome should not change, just mere changing the orientation, because their location in the 3D space or in whatever space we are considering, that should not matter. While what should matter, what is the structure in the graph, right? So how we can do? So for that we, nowadays several graph convolution neural network came. So I will define the one first defined by the KFI. So that is like the overall idea was actually motivated by the our this FFTs, or this discrete Fourier transform, and how we apply FFT over that one. So whatever is the multiplications or the convolution operations actually in the spatial domain, when we talk into the frequency domain or the spectral, generally we call that into the spectral domain. So at that time they becomes simply the multiplications and or the additions of the frequencies. So same this philosophy was used in this methods to define the convolutions. So let's say we have some U1 and U2. So these are some of the two embeddings of the two different nodes, whatever we have. Okay, so we wanted to apply a graph convolution, simply the convolution operation between these two inputs. So to like provide these facilities, what we are using actually, so because we have the diagonal, the adjacency, so from the adjacency matrix, let's say A is the adjacency matrix, from A we can compute the degree of the node. So D is a matrix where it's a diagonal matrix, and on the diagonal, the degree of each node, how many edges are connected with each node, that number is defined. So if this is an undirected graph, so it's simply the sum of row-wise sum of the adjacency matrix and place on the diagonal that we can put. So D minus A is called Laplacian matrix. Now L, if we take the row-wise sum, that is 0. Okay. So because from the degree we subtracted the A, so we have this Laplacian matrix. So Laplacian matrix, if we take any this low rank approximation, let's say that, which is mainly the SVD kind of decompositions or the eigen decompositions we are using. So let's say, Q are the orthogonal basis or the eigenvectors of matrix L. So L is now a symmetric matrix. So we can get our this Q. So Q transpose is going to be the identity matrix at the end. Okay. So what we will do first, whatever feature vectors we have U1, we will project that onto the Q. Okay. So Q transpose we will gives us a projection into the spectral space. So means whatever the original feature vector we have, we are actually projecting that onto the eigen spaces. Then within the eigen spaces, we simply do the element wise multiplications within these two feature vectors. But now we need to give the convolution operation into the original space. Then whatever is the resultant vector, then we project back into the original space by multiplying with the Q. Okay. Although this will be computationally little complex, but after certain simplifications, so we can get this kind of structures which is computationally little efficient. So that is nothing but the simplification of phi itself. Then whatever nonlinear functions, so after convolutions, we apply some nonlinearity or the activation layers. So activation functions we can apply over that one, and we can define our new projections of all those metrics. So this way we actually define the convolution operations onto these layers, and thereafter we can stack those layers one by one, same way as we were doing in the previous way graph seg, where our structure was fixed. But here it can be like this graph convolution neural, this graph convolutional layer will handle all those things through projections and then restoring that into the original space. So that's how we define our convolutional layers, and then rest of the thing is same as in the previous case in the graph seg. But now coming to the another type of graph neural networks, so where sometimes not only the node embeddings we need to learn, but we also need to rank the links. So far what we were doing, so we were considering the edge, with all the edges with equal importance. Okay, so there was no consideration at all that how much a link is important or what is the significance of each link. So in this category, we have this graph attention networks. So where we are actually learning the features as well as the attention between these links. So let's say these are the initial links given to us, but we can say that, okay, some links are weak, some links are strong. So we should not give them equal importance. So initially, let's say even if we consider the equally, but at the end we should learn how much importance we should give to each of our neighbor. Okay, so now we with the regular networks, the graph attention networks also use another network which actually over our this whatever the transform features. On that one they actually learn simply the attentions alpha ij case. So whatever the features we have with the two nodes, then we jointly learn a softmax function over that one, which can give us a probability distributions. Okay, so when we are defining the node h1, okay, so all these embeddings of all those are actually used, but finally how strong they are and how much they are in the alignment with the h1, or how much they have the same nature as of h1. Based on that one, these probabilities of all those connections is actually defined. And this is simply the previous whatever we are learning, either through simply the graph neural networks or graph convolution neural networks. What are the embeddings? We apply activation functions, and whatever are those activations, then we apply this softmax functions. So at the end we get our probabilities, okay, of each connections also. So now we use these uh, probabilities of their significance or their importance together with the our convolution neural network. When we are applying weights, not only the weights, their importance, what is also a we are learning. So one network we are learning the features, then with that one we are also embedding the importance of the features, which is actually attained through a softmax layer which was additionally placed to predict the importance of that link. Okay, so this way we can actually and not only learning the features of the node, but also the importance of the node. And when we are learning the importance of the features or the feature vector of the node, then the significance of the link with each of the neighbor, we are directly incorporating that also within that one. So this way we can also learn the attentions on the edges, and finally with that attention the final features were also learned with that one. Okay, so wherever you wanted to you are concerned about the importance of the edge, then this kind of attention based graph neural networks you can use, and you can get both the features vectors as well as the importance of the link. Okay, so as we talk about so far that we have some initial features and some adjacency matrix, and from that one we initially learn only the features, then we also learn the attention on the edges. But let's say if at the start or in the input, both the embeddings of the nodes as well as the these features were also given, then we can also incorporate those information also within these networks in the same way as we are using in the previous one. So whatever is the edge features, so those we can use while we are computing the next layers. So those kind of embeddings also we can incorporate within this one. So edge embeddings you can also incorporate, as well as you can also learn the edge embeddings through the embedding based convolution neural networks. So now let's coming. So this one single framework of graph convolution neural network actually becomes very popular, because whatever task we wanted to perform, actually we can perform. So let's say whatever graph we have, so initially we have some graph and some feature vectors, then we actually learn the new features of the node, and then in the next hidden layer. So in the next hidden layer, further we learn the more better way, as like in a simple multi-layer perceptron we did, or in a fully connected neural network we did. So we keep transforming the features, and at the end we have very good features. Let's say that's represented through the Z for all the node vectors. And As we talk about, we can also incorporate the attentions on the nodes, sorry, attention on the edges, as well as we can also use the embeddings or the feature vectors of the links if they are available within this one. So let's say this is a generic way. Finally, at the end, you learn new features with all those informations from the given network. But let's say, what are the tasks? With the same embeddings, you can do different tasks. So if you wanted to do the node classification, you can simply attach a softmax on the ZN and you will get your final classification of the nodes. Okay. So, but if you wanted to do the classification of the graph, so you have multiple graphs with that same framework, you can learn those embeddings, but now you have embedding for each the node. So different graphs, you have different embedding on different node, but you need to do some kind of some pooling. Either let's say simply the average of all those feature vectors. Let's say in this one, what we did. So there are let's say n nodes within this graph. So we can take an average embedding of all those graphs. Or if we are also using the attentions of all those nodes, two nodes combining, so based on that we can combine. Or simply we can also use like pooling operations. So these are the features at 0, 1. These are the numeric value. We can pick the largest value with that feature. So max pooling kind of operations you can apply, and then on top of that you can apply softmax. Then you can do the graph level based classification too, once you have very good features of nodes. So both node level task as well as the graph level task you can perform. Node level tasks you can directly perform with the given embedding, while for the graph level task you need to compute a average or a aggregate feature vector through average, or through max pooling, or through whatever other aggregation function you are using. As well as this node embedding can be very helpful to predict. Okay, so let's say these are the researchers as per our current knowledge. So there is a collaboration between these nodes, but there is no information of collaboration. So can we predict the probability of a collaboration or interaction? Let's say if it's a molecular network, so whether we know this is there is an interaction, but can we also define whether there is an interaction within these two molecules or not? Or whatever other graphs you have based on that one, whether there is a link or not. That we can simply predict based on the some similarity matrix between these two embeddings, and some non-linearity we can apply over that one. So we can also predict the link between the two nodes if it's not already given. And this is actually widely used in the graph autoencoders to just first learn a lower or the compressed graph structure, and then again decoding that to the bigger network, where we need to actually predict both nodes and then their links. So much literature is available on the graph neural network, where they use different type of further strategies to train or to aggregate these features for doing different type of graph. And that's why these are like now becomes very popular, because whatever task you wanted to perform, either the node level or the graph level or the link base, you can perform that task. So, and not only where we can actually see the graphs, so people also widely use in the action recognition or computer vision based tasks. Like I also use, I gave some examples for the abnormal activity recognition and as well as the action localization. Okay, or action detection, where exactly in the video the action is performing. So wherever there is a graph or node, so now by default graph based methods are doing the localization also. So this kind of works are nowadays very popular. So where even whatever visual data you have and whatever activity is there, so you can represent that through this nodes, and you can perform so graph convolution further, because in the videos we have the temporal information also, how we can use that temporal information also within the this graph convolution structures. and then the similar kind of network architectures they are following, and finally we can predict the scores of the action, whatever present in the video. So now let's coming to our last topic, how we can tell whether there is a whatever features a graph neural network is learning at the end, that has some significance. So we propose this graph line. So graph line is a like model kind of agnostic way that how whatever is a given model, how we can define uh, uh, or whatever features it's actually learning, they are actually relevant to the class label. And not only that, whether they are able to identify the meaningful features when we mix them with the noisy features. Okay. So for that, actually, we applied this nonlinear kernel based lasso, which is called HC lasso, which is a widely used this nonlinear feature selection or method based on kernel similarities between different features. So what we did, so whatever like node we wanted to explain, whether its embedding is there. So what in the same way, certain neighbors we sampled, and their feature vectors we put into a matrix. And on that matrix, what we did, so we passed that through whatever neural networks you wanted to use. Okay, so let's say Z is the features which, sorry, we are actually going to make from all those neighbors. So at the end, we define their, okay, whatever prediction they are going to do at the end, means, or whatever features at the end they are doing, and we keep collecting all those into the Z vectors. Then there we apply this nonlinear features ranking method. So we rank those features, and let's say their rank is represented through beta. And what are the ranks of those features that we do? And just to know that whether the feature is also identifying whether certain feature is relevant or some noisy. So we added certain noisy features also there. So now if you see within these architectures, we use several other explanation models also there. So lines and GNN explainer, greedy, and some random feature selection based methods which were previously used to explain. And now we are applying that. Now you see how many these noisy features our model identified correctly. So all the different models are compared here. So the green one was our model, which actually gives 0 score. So here this is the score 0, and thereafter some higher score that this feature is relevant. So to all the noisy features which are actually not learned but instead we added, so our model actually identified, okay, this has no relevance with that one. So that says that, okay, so now whatever is the feature actually truly has some correlation with the target variable, we are going to pick that only. And based on those whatever features actually trained or the given that, okay, this particular feature has this much importance in performing this particular task, we can catch that one. And based on those features, which model is actually learning more relevant features, we can define, okay, so the information is relevant or not. Okay. So just to conclude my talk, okay, so here we talk about, like, first of all, how we can represent the different kind of graphs in various domains, because in almost every domains we have graphs and its meaning is different. Okay, so but once whatever knowledge is there, so graph becomes some kind of like standardized in, okay, so we have node set, or some edges are there, or features on the node, features on the edge. So this kind of information we can do. Okay, so now you in one domain you can have one information, while not others, while you can use all those things. And also when they are not there, so let's say links are not there, so you are simply using the undirected kind of adjacency metric with 0, 1 only. But if you have weight, you can also use that weight with that one. We also see that how in the early days we used to apply graph kernels, which comes under this shallow learning techniques, and they were performing very well when our sample sizes are very, very limited. Still, they are performing much better than the graph deep learning based methods because they are data hungry. So we need very large data. When we have large data sets and very, very complex structures. So deep learning based, this graph neural networks or graph convolution neural networks, they are giving us the state of the art performance. Also, now we have several tools, especially recently we developed this graph line, which can dig out the information, whether the features trained by a graph neural networks are random or they have very high correlation with the target variables. Okay, so this kind of tool can be used to explain this graph neural networks. Okay, so that's all from my talk. Thanks very much. So if you have any questions, please ask.
Participant, any questions?
Yeah, I have a question.
So, yeah, madam. Hello, sir. Dinesh, sir.
Yeah, I can see.
Hello, Professor. Thank you for a second explanation of graph neural networks. I wish to know what kind of sampling technique that you would suggest for the contrast to loss function you were showing in the beginning of the slides. I think you named it as unsupervised learning loss function.
Yes.
Yeah. Can you shed some light on the kind of sampling techniques that are suitable here?
So you can see my slide again, right?
Yeah.
Right. You are talking about this loss function or the
Yes, sir. That, Professor, how do you do the sampling so that it's like a contrastive loss function, right?
Right.
Yeah. Can you
so,
just?
This loss function, actually the sampling when you are talking, so sampling is applied here. So you can see my cursor.
Yeah, that is to pick up neighbors, right?
Yes. So sampling is actually to pick up the neighbors.
Yeah.
Right? Now here, when we are talking about this equation, so this is actually, you can see that, okay, this CD kind of loss function is used. So here, it's simply, let's say ZU is the node where we are actually applying the loss functions, right?
Yeah.
So it's for all of your nodes individually you need to apply. So at a time. So this becomes your now the current node on which you wanted to apply the back propagation. So whatever it's this vector feature vector you applied, now with that one you are going to apply. Okay, so that sampling strategy you can decide. Either it can be like fixed. So whatever node we are actually explaining as of now, let's say this is the ZU U node whose embedding we are using. We can use its neighbors, or either from the certain neighborhoods, if you have certain information. Okay, so this node is actually not connected with this one or that one kind of things. So that kind of information. So that anyway in your adjacency you have that knowledge.
Sorry to interrupt you, Professor, but my question is actually in the second half of the equation, that minus Q into you are drawing a sample of Vn. Vn is sample from Pn of V, right?
Right. So that is like whatever here you are free to use whatever sampling strategy you want to do. That exactly I am explaining. So maybe this V, whatever we are here. So actually this is from the same strategy. So
okay.
So that way you can define whatever sampling techniques you wanted to use based on that one. So that is maybe you are doing the unsupervised things, but certain logical part you need to include within that one, whether these embeddings should be similar or not. So this can use as a kind of negative sampling, right?
Okay, yeah.
So the positive samples and that whatever are the negative ones, so you can use that. So this is simply the penalized. These are the like kind of nodes we know. Okay, they should not be in the correlation with the our embedding what we are learning. While there are some which can be like in the agreement. These are the neighbors.
And the Q is a learnable matrix here, am I right?
Right. I think this is not. This is some parameters. So Q is the parameters. So you can use that. Some kind of hyperparameters you can use.
Okay. Okay.
Hello, sir.
Yes.
So I have a question. Actually, you spoke about the STGCNN, Spatio-Temporal Graph Convolutional Network.
Right.
So, yes, sir. So actually, I have data of the patients, videos. From that, I have extracted the XY coordinates of each joint using human pose estimation techniques, which are available like open pose. And now I want to pass those pose this thing to the XY coordinate to the STGCNN. So I'm new to this field. So can you tell me how I can pass those things implementation wise to STGCNN? Like I've coordinated XY, I've got the
But
XY
your
coordinates.
point. So you have some human subjects, and its skeleton is with you, and
Yes.
it's like fixed point based skeleton. Individual frame wise you extracted, right?
Yes, sir. Yes, sir. Yes, sir.
Right. So you can refer the STGCN's way of graph formulations, and as in the start I said, so here actually the XY coordinate of the node, they does not matter. They can be anywhere, but their relative connections that matters. So these graph neural networks do not work on the their coordinates. Instead, that coordinates actually you are using just to formulate your graph. Okay, so all your nodes are there. So if you see, so within this one, one phenomena they took. Okay, so the respective joint is going to be connected to the respective joint into the next frame. So in one frame, it can, their XY coordinate can be different. In the another is different, but there is a link because this is the shoulder, so this is the shoulder. This is the elbow, so this is the elbow. So that kind of spatio-temporal links they are actually making. So similar kind of links you can follow and define your network. Now, whatever is the class label you are giving at the end, based on that, what links are actually important and which joint or which part of the body is actually should define that particular either action or activity or whatever is your objective. Finally, the backpropagation algorithm, through backpropagation, you will learn your features which are going to give you the attentions. So let's say here it's a kind of a running based things. So now the legs, here we should get more attentions. Obviously the hands are also moving, so there also we can get more attentions, while rest of the body, that is kind of parallel kind of things and not defining that much. Okay, so this way, whatever objective you have in your biomedical images, so you can use that in the same way. So XY coordinate just use to define the network. Once you define the network, they are simply the like nodes. They can be anywhere, but that structure our model should capture within that node.
Okay, sir. I understood what you were saying. So one more question. Can I get some good links on STGs? And sir, I've read this paper. Other than this paper, anything will help like to get more insights into this spatio-temporal graph convolutional network.
Okay, so I think now many this Python-based codes repositories on the GitHub are available, so you can search them. So even now, so many variations of this STGCNs came in the recent one, and few are still on the archives, but their GitHubs are there, so you can use them. So now people are using that for Parkinson's, not Parkinson's. Okay, so that means various kind of disease identifications which can affect our joints and other movement based patterns. So there are several works. I do not have a ready links, but if you search, you can find out those works, and even their codes are available.
Okay, sir. Thank you so much. Yeah.
So thank you very much, Dinesh sir, for your wonderful session. So I think we have to stop here.
Sure, sure.
So next
Thank
session
you
we will start.
all for attending, and thank you, Rakesh sir, for giving me this wonderful opportunity to interact with the
Yeah. Still,
generation.
students have some queries, or participants that have queries. So I think that they would mail you. Okay,
Sure.
so through the mail you may resolve their queries.
Okay, okay. Thank you.
Okay, thank you.
Thanks
Thank you.
again to everyone.